So this is a discussion on the material in section 6.4 and a last unit in section 6. So another unit on volume. I think it's a difficult unit. I think 6.3 and 6.4 maybe are some of the hardest material in the course, but that happens a lot at the end of of any college course. So we're going to talk about this shell method. 6.3 we talked about the disk method, the washer method, and the slicing method. Okay, we're going to talk about the shell method. And so you can think of a cylinder. Maybe we're just adding up the surface areas of just like a sequence of cylinders. So we just go out a certain amount R, and if you kind of and then just take that part of the cylinder and just unwrap it, you'll see that the surface area is 2 pi RH, and then times the thickness T. And again, if you look at the cylinder itself, right? So we know the surface area of a cylinder is 2 pi RH. So if you look at the outer cylinder, yeah, it's 2 R is the radius of the cylinder, and the height is the same, right? So if we keep decreasing the R, we're just going to get just a little bit smaller cylinder. So we're just adding up all the surface areas of the cylinders that make up this kind of big, the total cylinder. I'm not sure if that makes sense or not, but we're basically we're just adding up surface areas of cylinders to get this kind of solid, to get this one solid cylinder. Okay, and so here's the formula right there. So we know this the surface area of a cylinder is 2 pi radius times height, and so if we did that in terms of integrals, it's the integral, yes, and so and yeah, we're integrating along the from the beginning of R to the end of R. Okay, so it's 2 pi integral from A to B of the radius x times the height f of x dx. Okay, so when we're rotating around, and this is when we're rotating around the y-axis. So when we're rotating around the y-axis, we integrate with respect to x. Now, if you did the same thing integrating around the y-axis, I mean the x-axis, you'd be integrating with respect to y. And I have a couple of examples. I don't know if there's any in these notes right here. So there's a few examples in here. Again, someone wrote these notes for me, but I have some examples that I did on my own, just which I took from the homework. Okay, so let's say we have, first of all, let's see all these problems, 6.2, 6.3, 6.4. 6.2 is about finding area, 6.3 and 6.4 are about finding volume. This graphing is critical. If so we want to get some idea of what we're trying to, either what the area looks like or what region we're trying to revolve around a given axis. So, okay, so in this case, we're graphing y equals sine of x squared. And then, and so that I think we can graph with our calculators. X equals 0. So we start from x equals 0 and we go to x equals pi and the x-axis. So, um, um, so you get this blue region right there. And we're going to revolve that around the y-axis. So when we're revolving around the y-axis, we're going to integrate with respect to x. Okay, so the radius, so you just go at any given amount, right? And that's your radius, and that's x. And then the height, I guess I should have gone more like this to the top of the curve. And then here, and then so this would be your radius, and that's just x. Can't really spell radius, can I? Let's try to do a better job here. Radius, and then here the height is just f of x. So this is, I think, so in terms of the shell method world or the cylindrical shell method world, this is one of the easier problems when you were revolving around the y-axis. And so, yeah, so and then the limits of integration are from 0 to pi. Okay, so, and, oh yeah, I'm sorry, 0 to the square root of pi, right? So the integral so we're just setting up the integral. The volume is 2 pi, integral from 0 to square root of pi. The radius is x, and the height is sine of x squared. And so, yeah, so we would just be kind of finding the surface areas of all these cylinders. So if you actually went out another x, right, like to here, the radius would be different, and of course, in this case, and then also the height would also be different. So we're just adding up the surface areas of all these cylinders. And you actually have to do, this is the volume. So this is how you set up the problem. And then you just use a change of a variable formula, you let u equals x squared, du equals 2x dx. And in this case, we went back to we integrate with respect to u and then actually substituted x squared back in. So you could actually just, integrate directly from sine of x and just do it, just change the limits of integration. Okay, let's just do one more here, and then I'll look at the examples that I took from. This is actually this is a harder one. Okay, so again, we're revolving around the x-axis, but okay, so what makes this harder is that the lower bound, okay, so we have this curve, y equals x cubed plus x plus 1. Okay, but the region is being cut off by y equals 1, so it's that yellow area. So the height is x cubed plus, so the height, and again, it's actually right here, I don't have to repeat it. Okay, it's x cubed plus 1 minus 1. Okay, so in this case, which turns out to be x cubed plus x. Yeah, so here's your height. Oh, this doesn't print very well. Oh, here we go, students. There's your, still not printing very well. Oh, here we go. Sorry about all this. So we'll skip this. I'm trying to write this and my computer's giving me a hard time. Okay, so maybe that's mildly entertaining, my problems. Okay, so this is the height, and then this is the radius. And then how do we know the limits of integration? Well, we're told that we're going from 0. So again, you have to graph the region. So we graph x cubed plus x plus 1, y equals 1, and x equals 1. And so we're going to the right as far as x equal to 1. And so we're going from x equal to 0 to x equals 1. And then you just compute that integral. But basically, we're just setting up here. So we can actually even do one more here. So it's even a little bit more complicated here, this area 3, where again, so now the radius, we're revolving. I think this is where it starts getting a little bit harder when we're not revolving around one of the, our friends, the x-axis and the y-axis. But in this case, we're revolving around the line x equals 2. And I think that makes it a little more challenging. But once again, the height is the same. So it's the exact same region as number 2, y equals x cubed plus x plus 1, y equals 1, and x equals 1. Instead of revolving around the y-axis, we're revolving to a line parallel to the y-axis, x equals 2. The x-axis is y, x equals 0. Now we're revolving around x equals 2. And so now the radius is different. What is the distance? So here is the height right here. So here's our height. What is the distance of the height from the axis of revolution, right? So it's 2 minus x, right? So this distance is, sorry, students. This distance from here to here is x. Okay, so it's 2 minus x. So in this case, the radius is 2 minus x. So I think this is what makes some of these the solids of revolution difficult. It's just what is r and what is h, or this is for the shell method. It's just fine. It's just, or what, which is the inside function, which is the outside function, again, the washer method. But just visualizing the problem is really I think the hard part, or the creative part. Or I could say the really fun part. Okay, so anyway, okay, so now I'm not going to do any more problems from here. So let's just see. I posted these problems online this morning. Okay, so here's a few from my lab. Okay, so so this one, what do we revolve? Oh, so again, we're revolving around the y. So the students in the cylindrical shell world, we like problems like number 5. This is about, to be honest, I'm not saying it's easy. I'm not saying it's the easiest that we're going to get. It doesn't come any easier than this, because we're revolving around the y-axis. We're actually even given the regions drawn for us. So the concepts are, I'm not saying the problem isn't hard or these concepts aren't hard, but you're not going to, this is what would be considered an easy problem for this unit. Okay, so we're given the curve y is 13 over 1 plus 13x squared, okay, and and we're revolving around the line x equals 0, and we're gonna, so anyway, let's look at the region. The region is bounded by x equals 0, x equals 1, the line y equals 0. Yeah, so that's the x-axis, y equals 0. Here's x equals 0. That's the y-axis. Okay, and so so again, so we go out at distance x, right? So the radius is x. So the distance, and so the heights are given by by f of x, which is parallel to the y-axis. And the distance of the height from the axis of revolution is x. Okay. So the height, so the function, the formula for the function gives us the height, and the radius is just x. And again, we're gonna so we're rotating around the y-axis, so we're going to integrate with respect to x. Okay, so setting up so the surface area, let's say we take this cylinder right here. Let's say this is the height of our cylinder. And then here, we go out some x here. The radius is x, the height is f of x. And so the surface area of the cylinder is 2 pi radius, which is x, times the height, which is 13 over 1 plus 13x squared. Okay, so, and then we just integrate this from 0 to 1. We take this, formula here, just integrate with from 0 to 1. And then, we'll just use substitution. So this is kind of set up nice so we can do substitution. So let u equal 1 plus 13x squared. Du is 26x dx. We see in the numerator, we have 13x dx. So we have 13x dx is du over 2. Okay, so I'm going to change the limits of integration. So when x is 0, we just plug into here, we get 1 plus 13 times 0 squared. U is 1. When x is 1, 1 plus 13 times 1 squared is 14. Okay, there's no need to go back to the original variable if it's a definite integral. Okay, so we end up with, okay, so what do we get here? So we just replace, so the, right, so I can't keep all of this on the screen at the same time, but 13x dx is du over 2, and then the denominator, we replace that denominator, 1 plus 13x squared, the inside of the parts in the parentheses, we replace it with u, so we get du 1 over u squared du over 2. Of course, we still multiply by 2 pi, but now the limits of integration are from 1 to 14. There's no need to go back to x. Okay, so then, and just do a little simplification, cancel out the 2's. And so now it's, the antiderivative is minus pi u to the negative 1, and from 1 to 14. And now we just, it's minus pi over 14. So minus pi, you get plus pi, and you get 13 pi over 14. Okay, so that's our first problem. And then 9. Hello, problem 9. Okay. What is problem 9? Oh, we have 2. Oh, no, we're supposed to guess here. Okay, so let the region bounded by, let R be the region bounded by the following curves. If we were in the classroom, I'd ask a student to read this. That's what you, instead of me kind of doing all the reading, because I can't even read this. Okay, let me try again. Let R be the region bounded by the following curves. X is, we have one of these sideways parabolas. So that, and again, if you're having a hard time with these, like the x equals y squared, just graph y equals x squared to get some kind of visualization. Okay, so so it's this concave up parabola, and we're just kind of looking at it. If you kind of turn your head sideways, it looks like, if you make the y, turn your head sideways and make the x-axis, the y-axis looks like the x-axis, then it's really familiar. Anyway, but the one thing, students, graphing is critical. You need to know what the region looks like that you're trying to, we're trying to generate this solid, and you need to know what the region looks like. So it's x equals y squared over 2, and then we have the line x equals 0, which is the y-axis, and then the line y equals 7, right? So that horizontal line, that's y equals 7, and then the y-axis is x equals 0, and then the kind of thing that looks like a parabola is x squared, or y equals x squared over 2. Okay, so then now in this case, what are we rotating around? Okay, the x-axis. Okay, so students, this wasn't in the notes. When you rotate around the x-axis, you integrate with respect to y, right? the cylinder height is changing as we go up and down the y-axis. So we're going to integrate with respect to y, and so the distance of the cylinder height from the axis of revolution is given by y, and the cylinder height is we go out some distance x, right? So the cylinder height is y, and then the radius is y, and the cylinder height is given by x, right? But x, and let's just express x in terms of y, and oh, students, I just realized here, I got to correct this online too. I wrote the wrong curve. I think I'm just going to fix this right here. I think it's x equals y squared over 2. Okay, so that's better. Okay, so that's x equals y squared over 2. Okay, so yeah, so the cylinder height is, we go at a distance x. X is just y squared over 2, and the height is y. Okay, so so let's continue here. So the region is revolves around the x-axis. Integrate with respect to y. Yeah, so the distance of a cylinder height from the axis of revolution is y, because the axis of revolution is the x-axis. The cylinder height is given by x equals y squared. Okay, so the surface area is 2 pi. So y is the radius. Y squared over 2 is the height. And we're multiplying that by 2 pi, so the 2's cancel. So so it's just pi times y cubed. So and then the limits of integration, I think we're told that it's yeah, because we're told that the region is bounded above by the line y equals 7. Yeah, so we're going from 0, 0, here to 0, 7. So the limits of integration, where am I? So the limits of integration are from 0 to 7. So so the volume is the integral of pi times 0 to let me say again, the volume is pi times the integral from 0 to 7 of y cubed dy. And so this is, now it's pretty straightforward stuff from the previous unit. So it's a pi y to the 4th over 4 from 0 to 7. So, you know, we just evaluate that antiderivative at the upper and lower limit. And even though I know that at the lower limit it's 0, I still write that in so I don't get into a bad habit of not writing the lower limit. So I get pi, so we get pi over 4 times 7 to the 4th minus 0 to the 4th, which is 2,401 pi over 4. Okay, so okay here. Okay, so should we go to the next problem? Okay, yes, I think we should. Okay, the last one. Oh, you can stop listening at any time though. You know, it's not like a classroom. Yeah, I'm supposed to take attendance when I'm in the classroom. People take notice when people leave. But okay. Oh, so this is kind of a fun problem. This is, yeah. So this is the grand finale of our volume section. Okay. Let R be the region bounded by the following curves, and so we have y equals x. That's, you know, just a line at a 45-degree angle. And then we have the curve y equals x to the 123, and it's in the first quadrant. So students, the most important thing is not the most, and we're revolving around the x-axis. Okay, so and so again, so which means we're going to integrate with respect to y, right? Okay, so did I actually graph? Yes. So again, graphing is everything. And so the one thing is that when you're in between 0 and 1, x to the 1 over 23rd, x to the 1 over 23rd is going to be greater than x. Just like the square root of x is greater than x between 0 and 1. So like the square root of 1/4 is 1/2. Yeah, so then when for x greater than 1, then the square root of x is less than x. Okay, so graphing is everything. We need to know that in the graph, that the graph of y equals x to the 1/23rd is higher than the graph of y equals x. Okay, so we're going to do two. I guess what makes this really fun is we're going to do, it's a challenge. We're going to do this 2 ways, and then we want to make sure that we get the correct answer, because remember, the answer should not be dependent on the method of solution. Okay, so we're rotating around but the washer method, you're rotating around the x-axis. We're going to integrate with respect to x. Okay, so in the cylindrical shell method, we're rotating around the x-axis. We're going to integrate with respect to y. Yeah, okay, so, so it's the washer method because we're gonna rotate the area bounded from 0 to 1. So the upper curve is y equals 1/23. So we're gonna rotate that around the x-axis, and then we're gonna subtract off the volume that we get by rotating the line y equals x around the x-axis. So the area revolved around the x-axis is um, I should say, yeah, okay, anyway, we get pi times x to the 1/23 squared minus pi x squared. Yeah, so we're just, yeah, so, yeah, so, yeah, so, yeah, so like this area alone, so we're gonna get, when we revolve around, we're gonna get a circle. Okay, so we're gonna, so the outer circle is pi r squared and the inner circle is pi x squared. Okay, so what you get is the area of the outer circle minus the area of the inner circle. And so you get pi times x to the 2/23 minus x squared. And then and then to get the volume, we just add up all these areas. Okay, and so, and then and so the lines intersect at 0, 0 and 1, 1. So the limits of integration are from 0 to 1. So we get pi from 0 to 1, x to the 2/23 minus x squared dx. And now it's just something from the previous unit. We just use the power rule, add 1, and then divide by the exponent. So I think we can, yeah, so we get x to the 25th over 23 times 23 25ths minus 1/3 x cubed. And again, the limits of integration are from 1 to 0. So of course, in this case, the lower limit is going to contribute nothing from 0. I still write it in. So because I have seen students get into this bad habit of only evaluating at the upper limit. Because so many of the problems, the lower limit is 0 and doesn't contribute anything, but just make sure you don't forget to subtract off the lower limit. And it turns out we get 44 pi over 75. All right, so that's using the washer method. Okay, now the shell method, we're going to rotate around the x-axis. So so the heights, so we're going to integrate with respect to y. So the heights are going to be are parallel to the axis of revolution. Okay, so and so here I have this, I graph this again. And okay, so we're going to go up a given, so the radius is y, right? So we're integrating with respect to y, so the radius is y, right? So we go up, now and what we have to do, what is the height? Okay, the thing is, to get the same y, we're going to go out a different amount x. So, in this case, so for the curve y equals x to the 1/23, we're going to go out a different amount x to get to the same height as when we go to go up a height y on the curve y equals x. Okay, so the cylinder height, that's horizontal. It's parallel to the axis of revolution. So and so it's actually, we go, so you see here, we're subtracting off, this is from, that's from the line. And then this is from we subtract off the amount of x from the curve y equals 1 to the x to the 1/23. And you really need to visualize this, right? Because you see that we have to go out more x. We have to go out a further amount x to get to the same y for the straight line versus the curve y equals 1 for the curve x to the 1/23. Okay, so the cylinder height is x minus x to the 1/23, and just express that in terms of y. We get so this is from so for this is for the straight line, x and y are the same, and let's see here. And the other one we have, how can we express x in terms of for the second function? Yeah, so we just have to raise x to the both sides of the 23rd power. So let's go back down here. If we were in school and we had the boards up, I could have all this, and I wouldn't have to go up and down here. Okay, so the cylinder height is y minus y to the 23rd. Okay, and then the cylinder radius is y. So the surface area of the cylinder is 2 pi y times y minus y to the 23rd. And so let's just integrate this. And so we get 2 pi times y to the, times y. So this is the radius and this is the height. And now it's pretty straightforward integration. And I'll let you just look at these steps. And you get the same thing, 44 pi over 75. And I think I'll stop the recording if I can figure out how to do it. Okay, so.